Hey everyone, Mr. Fransky here. Today we're going to be talking about section 1.7. It's about mathematical modeling, but I really just think about it as being mathy. Mathy is a super technical word, obviously, and this just kind of sets the stage for some of the visualization and graphing techniques we're going to be using for the rest of the year. And it's important, I think, to be able to take this kind of stuff seriously because a lot of this is kind of what made me want to be a math major, just kind of visualizing how math makes us encounter our world in different ways. So let's see some of the vocabulary we're going to be looking at. So mathematical expression, math modeling, and visualization are kind of the things we're going to be focusing on today. So first, I want to just try doing some manipulation with some variable equations here. So if you want to give this a shot, you can. We're going to express the area of a circle in terms of only the radius. So let's do the radius together. So the area of a circle, remember, is pi times the radius squared, right? So see if we can come up with one for using just the diameter or the circumference. So let's say we don't know the radius, but we know the diameter or the circumference. How can you come up with the area? Now let's give that a shot. So if I know the diameter, well, it's easy to get the radius, right? The diameter is just equal to 2r. Usually what I would want to do is just solve for r now. So that means that d over 2 is equal to r. So I'm just going to sub that in for the r right there. So the area would be pi times d over 2 squared. Okay? So now if we know the circumference, remember the circumference of a circle is 2 pi r, or pi times diameter, either way. So if I solve this for r is c over 2 pi. So I'm just going to put that in for here again. So I have the area will be pi times c over 2 pi squared. And you can just leave it like that, right? You could square the c, square the 2 pi, and you could have one of the pi's cancel out, but I would just leave it like that. So if you know the circumference, that'll give you the area of the circle. Kind of cool. All right. So we're going to take a look at a visualization technique here, and I'm actually going to lead you on what I think is kind of a cool little exercise. So let's say you have an 8 by 15 inch piece of cardboard. 8 inches by 15 inches. So the question is, how can you make a box? So there are lots of ways you can make a box out of a piece of cardboard, I think, but I think the easiest way is if you cut out little square corners. Cut out little square corners like this. Alright. Now, if I erase the lines here, it's going to erase the whole thing. But let's say I cut out those corners. I'll just redraw them. So we cut out these corners. We're going to end up with something that looks like this. Okay. So we cut a square out of each side. Now what we can do is we can fold along these dotted lines that I'm making right here. So if you fold up those flaps along those dotted lines, you're going to end up with a box that looks something like this. Okay, so there would not be a lid, there'd be a bottom, right? This would be our bottom right here. And then these sides, like this side right here, would be this guy right here. Let's call that Y, right? I guess we'll put it in the front. I don't know, call it Z maybe. Okay, so that front would fold up. So if you fold it along those dotted lines, you end up with this little box over here. Now the reason I say this is really an exercise in visualization is because some people have difficulty visualizing this. And so if you want to try this, this is something that we actually talked about in psychology back when I had Mr. Simpson. And there are different levels where people can kind of think about this kind of thing, about like visualizing this kind of an idea. But if you want to do this, just close your eyes. And I want you to imagine a shoebox. So there's a percentage of the population that can't even see the shoebox, right? They just can't, they have trouble visualizing that in their mind. And this is something you can teach yourself. And the more that you practice with it, because I'm a weird nerd, I practice this kind of stuff a lot. But if you think about a shoebox, so you can think about it, right? And you can kind of see the lid on top, and maybe you know it's a specific kind of shoebox. So now imagine feeling the shoebox. Maybe it's that smooth kind of cardboard. You can feel the edges, feel how sharp those corners are. Now, this is where people start to get lost a little bit. Imagine picking up the shoebox and turning it in your hands. Can you see the bottom of the shoebox? Can you view it from different angles? Can you look at it from the top, from the front edge, from the corner? Can you see all those different angles? Now, this is one of my favorites. Imagine taking the opposite corners of the shoebox in your fingers, like the furthest corners apart, and spinning it. Can you feel how it's kind of off weight Can you feel like how the shoes might shift inside if they're in there? I love doing stuff like this, and you can go deeper with it. There are lots of levels you can do with this. Like, can you imagine your favorite food right now and how it tastes? Can you imagine how it smells? You can kind of train your different senses to be able to have these experiences without them actually happening. Okay, so open your eyes if you haven't already, but just this idea of visualizing these things. I'm a very visual person, but I think for some people this is difficult and challenging. So coming up with problems like this can be kind of tough for people, but the more that you do it, the better you get at them. So not a big deal. So right now we're just talking about, we have this piece of cardboard. We've cut out these square corners, and we're folding them up to make a box. So let's see if we can get some math in here. So first we're going to express the volume of the box, v of x, in terms of x. So what happened was, let's see if I can draw that shape again. Won't be, oh, that was totally wrong. Let's see here. There we go. That's better. Okay. So the whole thing here was 15, and the whole thing here was 8. So what we're going to do is we're going to cut square corners, cut squares out of all the corners of length x. So let's say that's x right there, that's x right there, that's x and x, x and x, and x and x. So each square has a side length x that we're cutting out. Now we're going to fold up those edges, right? And we said it's going to make this box. Okay, so we've got this box with no lid, and we want to express the volume of the box in terms of x. Remember, the volume of a rectangular prism like this is just length times width times height. And let's think if we can see what these are going to be. So the original length was 15. Is it still 15 though? Well, no, because we took some away, right? How long is that actually going to be? So it was 15. How much should we take away? We took off x from this side, and we took off x from this side. So that length is 15 minus 2x. The width is 8. How much should we take away? 1x here, 1x here. That's 8 minus 2x. And our height, when you fold up these flaps, think about it. That x right there is going to correspond to that height right there. So that's just x. So if I do length times width times height, v of x is going to be 15 minus 2x times 8 minus 2x times x. That is our volume. Okay. Now they ask us to talk about domain. So obviously I want x to be greater than 0, right? X has to be greater than 0, because if x was 0, I would have 0 height, I would have no volume, right? This x right here would be 0, I would have no volume. Now let's think about the biggest x can be. Well, this side I have lots of material that I can take away from, but this side here, the 8, it's a little bit shorter, and I can only take away so much. If x is 2, if x was 2 on each side, I would have, what, 4 inches left in the middle? If x was 3, I would have 2 inches left in the middle. But what if x is 4? If x was 4, this part right here, this 8 minus 2x, that would be 0. So I think that x has to be between 0 and 4. We can do less than or equal on each as well, because then it would just have a 0 volume if it was equal to either one of those. So x got to be between 0 and 4. All right, so next up, we're going to use a graph to determine the maximum possible volume of the box. So I'm going to go to Desmos here, and so we're going to use a graph to determine the maximum volume of the box, and also what length we should cut to make the corners maximize the volume. I'm going to keep those. So I've got a graph ready to go here. So I'm going to graph v of x. So v of x, if we come over here, was 15 minus 2x, 8 minus 2x, and x. So I'm going to do v of x equals 15 minus 2x times 8 minus 2x times x. Okay, so now we see we've got some kind of a cubic polynomial here, which makes sense. We have 3 x's. And I'm going to change it just for the domain that we want, just from 0 to 4. So I'm going to click the settings here. Go from 0 to 4 on the x-axis. Now it looks like we're not quite high enough on the y, so let's make our y's go a little higher. Let's make the y's go from like 0, because we're only concerned about positive volumes. So 0 to, like, I don't know, 50. Is that enough? Not quite. Let's go to 100. There we go. Now you can see what's going on. So I zoom out just a little bit. So we see between 0 and 4, depending on how much you cut out, right? Because this is v of x on the y-axis. This is telling me, like, if I cut out 1 inch on each edge, for a square of size 1 inch, the volume is going to be about, what is that, like 80? Somewhere around 80, 50, 60, 70. Yeah, about 80. Okay, if I cut out 2-inch squares, my volume is going to be like closer to 90, right? So this is telling me on the x-axis how much I'm cutting away, and on the y-axis how big that volume is going to be of that box. So, what we're going to do is determine the maximum possible volume. Well, it looks like the maximum volume is going to happen right up there. And if you click on this for Desmos, it'll tell you what that is. So the maximum volume looks like is 90.74 inches cubed, right? Cubic inches for volume of a box. And they're saying, what length should I cut out? That's the 1.667. So it looks like 1 2/3 inches will give me that maximum volume. Kind of cool. Okay, so let's write that down. So I think that we said that the maximum possible volume was, what was it? It was like 90 point some, was it? 90.74 cubic inches. And the x value that made it the biggest was 1.6 repeating, which is 1 2/3, or what, 8/3? Yeah. Nope, that's a lie. 1 2/3. Let's see. 3 and 2 are 5/3. 5/3 inches that you should cut out from each corner. Cool. So as you can see, a little visualization, a little bit of modeling using an equation, but nothing too ridiculous. So what we're going to do now is we're going to take a look at sending a satellite dish in the mail. This is kind of a fun problem. I like this. Basically what you're thinking about is if you have a satellite dish that you want to send through the mail and you want to put it in a box, but you want to give that box some support so it won't collapse and it won't hurt the satellite dish, you might take a cylinder like this and you might set it like right here inside the dish. Okay, so how that would look in here, that'd be like right here. And you see how if you cut the dish at any point, like if you cut the dish right here, it would give you a circle. And this is kind of hard to visualize as well. I think this one's actually harder than the box one. But basically what you're going to do is you're going to take this cylinder, you're going to set it inside the dish, and it's going to hit right at the top. So that if you put this thing in a box, the box would cover right at the top of the dish, and then that circle would kind of support the top of the box. That's the idea here. Okay. So if you have trouble visualizing that, it might be worth taking a look at this a little bit and trying to figure out what that would look like. But basically that cylinder is just going to sit right in the top of the dish. So what we have here is, let's say we have a dish that is 24 inches across the top. And what we want to do is take a cylinder that is 12 inches across the top, and we want to know how high should it be. Okay, how high should it be if the height of the dish is 6 inches. So obviously the cylinder is going to be shorter than 6 inches, right? Because it's going to have to sit inside the parabola here. Okay, but this thing just 12 inches across, and the dish 24. So the question is, how tall does the cylinder have to be? Where should I cut this thing in order for it to sit in and just have the top of the box sit right on top of it? So for a problem like this, we talk about this in Math Team a lot, you should really make a coordinate axis. So what I have here is I did that. And here we see that we have our 12 inches on each side, so the whole thing is 24 inches across. And we have a height of 6. Obviously, this is not to scale, right? And the question is, if I have a 12-inch cylinder, so it's going to go 6 to the left and 6 to the right, how tall should it be? Okay. So to do a problem like this, what I'm going to do is I'm going to think about the points that are on this parabola. This point right here is going to be pretty important, right? I kind of want to know how high that is off the ground. Well, that's just the y coordinate of that point. So I want to know 6 comma, what is that y coordinate? And then if I find that, I can just subtract from this total of 6, and that'll give me that height. So what I'm going to do is I'm going to say, well, this parabola is going to have the equation y equals kx squared. How do I know that? Because this is just a scale change of the parent function y equals x squared. So there's going to be some number multiplied out here in front of x squared. I have to figure out what that is. To do that, I need to have a point. Well, it looks like I know this point's on it, right? 12 comma 6. So I'm just going to plug that in for x and y. So I have 6 equals k times 12 squared. 12 squared is 144. So I have 6 equals 144k. Divide both sides by 144. 6 over 144 equals k. Now let's see if I can reduce that. If I divide those both by 2, I have 3 over, what, 72? 72 is 3 days. That's 1 over 24. Okay, so I have y equals 1 over 24k squared. X squared, excuse me. So now I want to know, what is the y coordinate when x is 6? Well, then y is 1/24 times 6 squared. That's 36 over 24. You can reduce that. Let's see, divided by 12, that's 3 halves, which is 1.5. So this is 1.5. I need h to be the rest of that distance, so it looks like it's going to be 4.5 inches tall. That's kind of a tough problem, and it really has, it banks on you knowing the relationship between the x and y coordinates on a parabola. Okay, a little bit tricky. Might have to take a look at that one again. All right, so last one I want to do here is a pile of pixie dust. I've had students every year decide what they want it to be, and since I'm doing this in a video, I decided it's going to be pixie dust. It can be a pile of any kind of substance you want. I think the book calls it gravel. I don't know. But anyway, pixie dust is more important and more exciting anyway. So pixie dust is falling into a pile on the ground at a rate of 8 cubic inches per minute. So every minute, 8 more cubic inches. The height of the pile is always the same as its width. Interesting. So if the pile is currently 1 foot tall, how tall will it be in 1 hour? All right, so let's think about this. If we have pixie dust falling onto the ground, as it builds up, think about what kind of shape it's going to make. So I think it'll kind of make a shape like this, right? It'll make a cone, right? And obviously pixie dust isn't real, but any kind of a dust that you have, Kool-Aid, dust, why not, gravel, whatever this is, right? Any kind of thing that's falling onto the ground is going to create that kind of a cone shape. Fun fact, that angle never changes. No matter, it depends on the substance, but that angle will always stay the same. It's kind of cool. So telling us that our height is always the same as the length, the total width of the base. But I think that's actually not what I want. So what I'm going to change here is the height is always the same as its radius. The way I first did this problem is with the radius. I didn't want to give it away right away, though, which is why I didn't have it there. So what we're going to have here is the height is going to be the same as the radius of the cone. So right here, this distance is also h. All right, so we have a height, we have a radius that are the same. So they tell us the pile is currently 1 foot tall. How tall will it be in 1 hour? So some things we need to know here. The volume of a cone is 1/3 pi r squared h. It takes up, so a cylinder is just pi r squared h. It takes up 1/3 of its containing cylinder, which is kind of cool. What else do we need to know? Let's see, 12 inches in a foot, 60 minutes an hour. Those are important things. So what we're going to do right now is we're going to figure out what the current volume is. So I'm going to call it VI, V initial, the initial volume. So the initial volume here is going to be pi, 1/3, pi times r squared. Well, r is the same as h. So I'm going to do 12 squared times the height, which is also 12. Okay, now I'm going to do a little bit of magic here. So 12 times 1/3 is 4. So this is pi times 144 times 4. That's our initial volume. Now what I want to figure out what my final volume is going to be. So the final volume, well, I started with this 4 times 144. Let's actually figure that out. That's going to be 400, and then 4 times 44. So we have 400, and then 4 times 44 is 160, 176. So that total is 576. So we have 576 pi. And then I'm going to add to that the amount that's going to fall in that 1 hour. So 1 hour is 60 minutes. So in that 1 hour, we're going to get 60 minutes times 8 inches cubed per minute. Make that a better N. Okay. All right. So 60 times 8, 6 times 8 is 48, so that's 480. So we're going to add 480 more cubic inches. Okay, so we started with 576 pi, and we add 480 because it's dropping at 8 cubic inches per minute. Okay, so now we've got to figure out what the height is at that point. So we know that this is equal to this formula. It's going to be 1/3 pi r squared h. But we know r and h are the same, so I'm just going to write that as h cubed, because it would be h squared times h, so that's h cubed. So now we just have to solve for h. So let's see here. Let's look, we're going to have to multiply by 3. So let's see, let's do this over here. So we'll have pi h cubed. So we'll multiply both sides by 3. So we have 3 times 576 pi plus 480. And then we'll divide by pi. So that's gone. And then we take the cube root. So h is going to be the cube root of 3 times 576 pi plus 480, all divided by pi. And if you grab a calculator to do that, I believe it ends up being about 12.98 inches. So in the course of an hour, even though it's falling at 8 cubic inches per minute, that's pretty fast, a lot of that ends up going towards making it wider. And it actually doesn't get a whole lot taller. I always thought that was kind of interesting. So that's all I've got for you today. A little bit long video here, sorry about that. But hopefully you were able to get some of this visualization and this math modeling down. These problems can be a little tricky, so make sure you give some time to the problems that you're given. Love you guys, that's why I'm here. Have a great day.